Thank you everybody for being here today. My name is Caleb Lowe. I am a staff machine learning engineer at Data.ai, and I'm really excited to talk to you about some of the work that we've been doing involving scaling MLOps for our organization. So some brief background, Data.ai is the premier provider of mobile marketplace data and ecosystem insights. What I mean by that is we provide mobile app KPI estimates across a variety of domains, including usage patterns, sentiment, user acquisition, monetization, all kinds of things. And one of our cornerstone products is our best-in-class downloads estimates. So how many downloads did any particular app get on any given day? These downloads estimates are produced using Ranks by Data.ai, which is the project I'm going to be describing today, among other things. And Ranks by Data.ai uses an ML model that uses our understanding and our quantification of the mobile ecosystem in order to predict and rank app performance. These ranks and downloads estimates are then used by our customers to benchmark their performance against competitors, to see how they're doing, how their competitors are doing. And while that might be a bit of a specific slice of work for the people in this room, in the spirit of the conference, Data Intelligence for All, what we're really going to be talking about today is not so much the particulars of the project, but the MLOps framework that we're using as a whole. So MLOps, that is machine learning operations. According to Databricks, this is focused on streamlining the process of taking machine learning models to production and then maintaining and monitoring them. It gives a variety of benefits, including efficiency, risk reduction, scalability, because these processes are agnostic to the ML problem or even to the industry. It's a set of practices that one can use in order to organize the machine learning landscape in an efficient, scalable way. What we're really going to be focusing on in this presentation is the development, retraining, review, and deployment process. But of course, there's the full loop as described here. The real challenge that we face at Data.ai is scaling our MLOps, which presents specific challenges. So the Ranks by Data.ai model, it has a bunch of features, but it is in and of itself a rather simple model. The technical difficulty comes from the combinatorics. We have to produce these models for a large number of countries, multiple metrics per country. Some of these models have submodels. So you can imagine submodel A, B, and C for metric 1, 2, and 3. All of this modeling is happening for one country, and then we're doing that for a bunch of countries. And you can really see that this problem can grow very quickly as we're adding more and more combinatorics. And maintaining all of this is difficult. The way that the combinatorics map onto our project is that we end up having 50,000 individual models that need to be retrained on a weekly basis. So the question becomes, how do we even approach model development, training, and maintenance for 50,000 models every week? And that's what we're going to be talking about today. Here I have an agenda, and I know a lot of people like taking pictures and a lot of the content. We are going to be getting pretty technical and getting hands-on. A lot of the content is available in this Medium article here, so feel free to follow along there, and you won't have to go through each of the code snippets through the bulk of the presentation. So in terms of the order of what we're going to be doing today, we're going to talk a bit about Pandas UDFs as an introduction. From there, we're going to talk about 3 tips for scaling MLOps using UDFs. Those 3 tips are to start small, to wait your turn, and to keep things clean. And then finally, we're going to be discussing some limitations with the particular way that this was implemented and what I'll describe. And we'll talk about some potential workarounds and extensions, especially when it comes to the difference between batch and real-time processing. All right, so let's start with our introduction to our Pandas UDFs. So the basics. Pandas UDFs are user-defined functions, UDF, that can be used on a Spark data frame. This is in contrast to the typical Spark UDF, which operates on a row-by-row basis. So there's a lot of flexibility using Spark UDFs, but there is an execution cost by having to iterate row over row. Pandas UDFs vectorize these computations and are more efficient because you're working in a column base instead of in individual rows. And finally, there's also Pandas function APIs, which these are similar to UDFs, but UDFs they produce a column, they take columns as inputs. Pandas function APIs work on an entire data frame and can return an entire data frame. This allows for custom aggregations and a whole bunch of cool stuff that we're going to be going into. Just for ease of nomenclature, though, we are going to be pretty much exclusively talking about Pandas function APIs, but I'm going to call them UDFs because it evokes that idea of user-defined function, and it just makes things simpler to say. But again, we're going to be focusing on these function APIs. So let's see what one of these looks like so that we can learn how to build these up and apply them in other situations. We'll start out by just writing our own grouped average function. This is a really simple example. There are obviously built-ins to do this, but this will help establish building blocks that we can use for more complex processing. So first, we'll start and create a sample data frame. Let's just take 5 rows, call them A, another 5, call them B, and give them random values. So this is what we're showing here. You can see that the B values has this arbitrary +3 offset. We're trying to establish that there's a difference in average, so we can see a difference when we actually create our group average. But these are just random numbers generated in a toy way. We combine these into a Pandas data frame and then create a Spark data frame from that. The built-in grouped average function is a simple group by and aggregate call. So if we want to use the built-in, we can do something like this. We can use our test data frame, group by our group, and aggregate and take our average value. And this gives us a data frame, which is being hidden by my commentary, but it's it's groups with a single float value indicating the average values there. Now let's advance this. Instead of using our built-in, let's define our own grouped average UDF. So really what we're tasked with there are 2 things. To recreate that table that was in the output, we need a group and we need our average values. In return, we need to return those as a Pandas data frame. So if we define our grouped average UDF, it'll take in a Pandas data frame. And because we're doing this group by operation, every value in the group column will be the same. So we can just pull the top value off of that to get our group identifier, and then use NumPy to get the average of the value column. And then we can assemble these into a Pandas data frame and return that. To then apply this function, all we need to do is specify a return schema using Spark types. So we can import our types and define our group as a string and our average value as a float. And then this plugs in really neatly just in the same way as the built-in averaging, where we take our test data frame, group by our group, and then here we just apply in Pandas instead of use the ag. So apply in Pandas our group average UDF, and then pass in our schema. And this reproduces the exact averaging data frame that we looked at and found using the built-in. So from here, we are ready to, you can see how the architecture of a UDF works, and we are ready to build upon this and build a model training UDF using these principles. So the first step to scaling, as I mentioned in the beginning, is starting small. So as we just saw, a UDF is only a function that takes in and returns a Pandas data frame. So here's the UDF that we just developed. And we can leverage the fact that this is just a function by extracting a Pandas data frame out of our Spark data frame and then running it through the function just as is on our driver. So what I mean by that is we can extract just one group, for example, group A, extract that to a Pandas data frame, pass that into the grouped average UDF function, and get just a single row as output from that, which we see matches the corresponding row from the previous slides. So what we can do is build out our more complex functions by taking a single group that we're interested in and developing the function just in Pandas in order to then parallelize it very easily in the next step. So let's see how this works. The Ranks by Data.ai project is based on our random forest. So I'm not getting too far into the details of that model, but it is a random forest. So we're going to use a regression example from sklearn to highlight the flexibility of this approach. So we'll just import fetch California housing. So we'll get the California housing data, convert that into a Pandas data frame and then a Spark data frame. And what we'll do is we'll also create some arbitrary groups. We're going to get high and low for target values above or below the median. So we'll add this column relative target. And when the target is above 2.5, we'll call it high. Otherwise, we'll call it low. I want to pause here and say that this is a very arbitrary example. This wouldn't be good practice because it would be peeking at your target variable. There's all kinds of cross-validation issues with doing this exactly as such. But we're illustrating a concept here. What we're doing is just creating arbitrary groups. So obviously there'd be more particular ways to do this in a production setting. But for now, we're just going to arbitrarily define our two groups here that we can train separate models for our high and our low values. And then finally, we'll extract one group for further testing. What you're not seeing below the text here is that we're filtering the low group out and converting that to a Pandas data frame, just like we did with the A group on the previous slide. From here, we can write our fitting function. We just pull out the group like we did before. We get the first value from our relative target column. Then we instantiate a random forest regressor and fit it with our features and our target column. Really straightforward sklearn stuff. And then from here, we add in the MLflow logging. So we start an MLflow run and then log the model using this syntax. And what we'll do is we'll name it something like California model this group, where this group will be either high or low, depending on which group is processing. The last thing we need is to return a Pandas data frame in order for the UDF to run. And so one thing that I like to do is to use the artifact path of the stored model as something to keep track of, and also just to give us something to return. So we can return our relative target, that is our group, and then the model path, which we can pull from the MLflow artifacts. Finally, we can test this function outside of on the Pandas data frame for the single group. So we can get that Pandas data frame we extracted, pass it through this function, and then again, what's hidden is a Pandas data frame that has a target and a path to the model artifact. And here, if we load in that model artifact and then generate predictions, we can see that they cluster on the diagonal. That is, there's a high predictive power from this model. Again, it's not cross-validated. That's a separate issue from what we're trying to illustrate here, and it can obviously be included. Right. So that was training the model for one group. There are some modifications that are necessary for group applications. The first and most simple one is nesting. So let's build out the PySpark code for training the model across both groups and see what happens with the existing version. So as before, all we need to do is to move from the function to the UDF as a return schema. So we'll define our schema, the relative target, the model path, both strings in this case. Group by apply in pandas, that's the structure we've seen so far. And if we look at what this is, we can see that our two groups both get trained models, and you can see that there are model paths pointing to those model artifacts, but they have a different run ID. The run ID that is between the slashes is different in this case. So what we can do is we can assign the same artifacts to the same run ID, get the organization done a little better by making some slight modifications. So here we have the function that we just wrote. We've broken out some space because we're going to add some stuff to it. But before we do, let's look outside of the function in the Spark side of our code where we have our Spark data frame. What we're going to do is we're going to first start the MLflow run on the outside of that so that we can add columns for the run ID and experiment ID, basically get those identifying information, and then call our UDF within that. What we can then do is then extract the run ID and experiment ID from that we added from inside the UDF, just in the same way that we do with the group. So we can grab the top value of run ID and experiment ID, and then start a nested run with those parameters. Otherwise, everything is exactly the same. And what this is going to do is it's going to produce the exact same thing that we saw in the last slide, but now the run IDs are going to match up. And then if you look at your MLflow UI, you can see the organization gets quite a bit more cleaned up. There is a second and sneakier issue that happens with the training at scale, and that has to do with the MLflow API rate limit. So if you start adding combinations and start training more and more and more models all at the same time, you end up getting 429 errors, so rate limit errors. and the model training will fail. If you have exceptions, it will still run through, but then you're only training however many models were within the rate limit. So there's some non-determinism there. So the idea here is that inside our UDF, what we need to do is add some kind of random jitter so that we are spreading out our logging over time so we don't hit the rate limit. But the first issue with that, we might think, okay, I'm just going to get a random number. I'm going to wait for some random amount of time before logging. And you can do that, but most random number generators will pull their seed from the clock time. So if you used a clock-based seeding and you have your driver node and it distributes the task among several worker nodes, worker node 1 is going to get a random wait time off of the clock. It's going to wait that, and it's going to train and log. But the other workers are also going to have the same clock time and therefore the same seed for their random number generator. So what you're actually doing is just adding a wait, but still stacking up all of your logging at the exact same time. So this simple random jitter isn't as effective because you're not separating out the logging the way that we're intending to. A better approach is to get a hash value based off of the partition ID or what your group is, so that when you have these 4 workers working on 4 different groups, the random weights are going to be different depending on which group is being worked on, and then that's going to separate out the training and logging in time in a way that, that prevents hitting the rate limit. If we look at this in code, again, this is the same training UDF that we've been looking at. We've added the nesting, but all we have now is we're going to add this chunk here. We're going to seed our random number generator with a hash based off of our group ID. So reset the seed, get a random weight value, and then use the time module to sleep for some random amount of time. So it's our random value times 5 seconds. That would give you, uniform distribution between 0 and 5 seconds of wait. Depending on how many combinations you're working with, you would increase that 5 to be something larger or smaller. That's where you can tune your overall performance based on the number of your groups. These are going to be much more likely to be unique and avoid the rate limit. So to summarize so far, we can use Pandas UDFs to parallelize arbitrary Pandas functions in Spark across various groups. Those UDFs can be developed by using a single group as a Pandas data frame before applying the function to the entirety of the Spark data frame. Nesting your MLflow runs packages model artifacts into a single run, which helps with organization. And MLflow has a rate limit, but this execution can be jittered to avoid getting errors. And finally, you can track where these models actually end up by returning a path to the model object in MLflow, because you need to return something in order to get the function to actually run through. So this is a handy way to track where your model artifacts go. I'll let that breathe for just a moment before we move on to the next section. All right, so after training, obviously we need to close the loop. We need to perform model inference. So we've stored our models, and now we need to pull them back in for inference. So we can build an inference UDF using our previous lessons, something like this, where we predict our California UDF. Here we extract the group just like before. We're assuming already that we've joined on the model paths that we produced by the training. So we have this model path column where we can pull off the model. The next chunk, we do the random weighting again based off of, by seeding based on the group ID and not based on the clock. And then once we've weighted our random amount of time, we load the model. The loading also has this rate limit. That's why we need to do it in both places. And then we do our prediction and then return the data frame with the prediction column added to it. And then we can apply this the exact same way as we did with the model training. Here, as I mentioned, we can join on our model paths from the training. This middle chunk here, it's available in the Medium article. It's available right here. It's just some boilerplate for adding a column to an existing schema in a way that is kind of safe against Spark's lazy evaluation. Depending on how and when things get called, sometimes if you try to just add a schema, things can get a little confused. So this is a way of kind of freezing a schema in a way that you can add it safely. And then finally, this bottom chunk here that's a little cut off is what we've seen before. It's grouped by apply in pandas, apply our predict California UDF. This Inference UDF does offer us opportunities for other hard to diagnose errors to come about. Luckily, we can also solve those. So one particular error that we run into is memory. So when we load the model within the UDF, MLflow is going to store that model object into the temp directory of the worker node, or it's going to store it into the temp directory of the node that it's executed on, which will be the worker node if you're doing this apply in pandas parallelization. But if we never clear that out after loading in the model artifact, as we're doing more and more combinations, we're going to just be adding more and more models into that temp directory. And depending on how many combinations you have, that you can end up completely using all of the memory on your worker node just in storing these no longer being used model objects. So because basically where you're going to end up is the number of groups divided by the number of workers. That's the number of model artifacts you're going to be storing on each worker. So if we have 50,000 and we only have 8 workers, it's going to be quite a bit. What we can do to get around this is to delete the model objects once we've used them for inference. If the issue is that there's too many of them, why not get rid of them as soon as they're done being used? So what we can do is use the OS module as well as leverage MLflow's load model input arguments where you can specify the directory that the model artifact gets stored to. So what we can do is set up our own temp directory. So within temp, we can set up a folder for the group that we're processing. And then inside the MLflow sklearn load model call, you can set a destination path. And so we can make sure that we're storing this model to that directory that we've just created. From there, then we run our prediction. We create the column with our predictions. And now the model is done being used. This is the point that we don't need it anymore. And so before we return our data frame, we can use OS again to remove everything that lives in that temp directory that we just created. So basically, we create a destination, load it to that destination, use it, and then purge it. So putting it all together, now that we've ensured that we've kept our resources available, we can rerun the Inference UDF in Spark and test that our models are working and running separately and in parallel. So we'll test this model output by making a scatter plot and keeping our 2 groups as separate colors. So here, up at the top, it's what we're used to seeing by now. We have our group apply in pandas, our prediction UDF. We'll take that output, our ZF with predictions, extract that out to pandas, and then make a couple scatter plots. We'll scatter the target against prediction for the high and the low group. And if we show this, we see our split group model performance. And there's a couple things to observe here. One, the models are doing well. Again, this is expected because we didn't do the cross-validation. This is a training accuracy, so on and so forth. But we're seeing this general diagonal trend where the predictions are following the target. But more notably, we see a trend break right in the middle where we separated our high and our low groups. So right where the pink transitions into the maroon, you see this vertical offset where things aren't perfectly following the diagonal. And what that indicates is that that discontinuity is showing us that we don't have one continuous model happening across the entire space. We are separately modeling our lower and our higher values. So, interim summary 2. The same parallelization techniques that we learned for model training can be used for inference as well. And in addition to respecting the rate limit, which we learned on the training side, the Inference UDFs also need to respect memory limitations and make sure that you clear out the model objects that you load from MLflow in order to prevent flooding of the temp directory that would seize up your cluster. And third, adding a column using an existing schema can be done. There's this particular way of adding them. There's boilerplate to avoid conflicts due to lazy evaluation. All right, we've now gone the full loop. We've used UDFs to train and infer. This approach does have limitations. There's some trivial considerations. I've mentioned this a couple times, but there's no cross-validation or other typical model selection processes in this talk. But this is trivial. This is all stuff that can be baked into the training or into a separate UDF. All of those typical model selection and cross-validation procedures can be incorporated into the UDFs that we've written here by just adding some more lines. You know, they're going to be more complex, but the process of parallelizing them can happen exactly the same way. Second, we didn't register the models. We kind of just kept track of in the runs where the models landed. But similarly to the cross-validation, this is also something that could be added into a UDF, where you could even have a separate registration UDF. And even if you have a separate registration UDF, you could do even more complex kinds of comparisons, like a challenger champion model comparison, to only update and re-register the models that need updated, or any other kinds of complex analytics or model retraining optimization. It can also be baked into here using the same principles. And what about multiple groups? Here we've only grouped across one column. Can you group across multiple columns? And the answer is yes. There's no difference in the procedure at all. You just need to incorporate the multiple groups into all the places that we identified our group name and like set our random number hashes, et cetera. But there's some more serious considerations, particularly for real-time inference. The Ranks by Data.ai project is lucky in that it runs on this weekly cadence, and it takes some time to run, but it's a batch processing procedure. So we don't run into strong time constraints. And that allows that rate limiting procedure especially to be, we can really extend that out for safety. But there are the retraining and inference times are quite long. So avoiding the rate limit, especially for large combinatorics, can be difficult. And so rate limit avoidance time becomes a limiting factor for real-time applications. Again, a similar question is how to manage 50,000 model endpoints. So another way of converting this to a real-time thing would be that once we've trained the models, host them all as individual model endpoints, but that would need to be managed. And you would think you'd need some kind of gateway or routing system to make sure the traffic for the right group goes to the right model based on the inputs that you give it. And that adds complexity. But one suggestion to approach this real-time approach is to use a PyFunk wrapper. This part is where we get a little more kind of speculative. But in general, a PyFunk wrapper is kind of a generic MLflow model object. It's kind of the most generic flavor. You know, it's not an sklearn, it's not a Spark ML, it's not a transformer. It's just a general PyFunk object. And this gives it a ton of extra flexibility on top of the specific flavors. And most key, they have a context. So when you host a PyFunk object as an endpoint, there's a load context method that gets called, and that can set up all kinds of things like imports or loading of models, and a ton of extra flexibility there. So that then when you go into the predict method, you can use the context that you instantiate, such as loading the high and the low models separately, and then route traffic to that model that has been loaded into the context. This becomes more complex as you add more and more because just having more objects in memory in the context is going to run into the same kinds of considerations about the inference that we were just describing. But the model wrapper is a very flexible construct that can be used for a number of similar use cases if they don't get super massive. And then the logging call is really quite similar to any other MLflow logging. All right, so what we've learned, thanks for sticking with me through all of this. At the top, we did a bit of an introduction to Pandas UDFs. We learned about the different kinds of UDFs, how they can pair with Spark UDFs, and how Pandas function APIs can be used to work on entire data frames and not just particular columns. From there, we introduced 3 tips for scaling MLOps using UDFs. Those 3 tips being to start small, to wait your turn, and to keep things clean. So develop on one group because you can then parallelize very easily once you've developed your model on one group. Waiting your turn means make sure you avoid the rate limit because that's going to hang up and you're going to get perhaps silent errors. And keep things clean, that is, clear out your model artifacts once you've loaded them and you're done using them. And then finally, we went over a few limitations. We talked about the batch processing versus real time and how batch processing is kind of okay in this approach because of these time constraints, but real time, that rate limit especially is going to be something that you're going to need to avoid. And we talked about one potential workaround and extension by wrapping these things into a PyFunc object. And a lot of this content we can find in this Medium article here. And the final thing that I want to leave you with is again, this is a very general procedure. This is something that is not specific to mobile app performance. This is not specific to ranks by data.ai. This is something that can be used really across the board. And as a part of that, data.ai is now a part of Sensor Tower. We've combined forces to really bring the best of mobile app performance. And so the ML techniques presented today, these are going to transfer to Sensor Tower just fine, but they can also transfer to anybody else just as easily. They're not even specific to any industry because this can be really used for any problem that involves grouped ML where you have a small unit that needs to be replicated in mass. And so as we push forward on Sensor Tower's mission to measure the world's digital economy, these skills are going to allow us to build and scale brand new ML applications to help bridge the gap between companies and customers. Thank you all for your attention. I really appreciate it.